Section 8.7, Linear Inequalities. In the next two videos, we are going to be looking at how to use what we call set builder notation, how to use and understand interval notation, how to solve linear inequalities and compound inequalities, and then how to apply those to solve word problems. In the first video for Section 8.7, we're going to spend time looking at just a lot of terminology and definitions, and then also a little bit of the notation for writing things in sets. So let's look at just first of all some definitions. What do we mean by the term set? A set is a collection of objects or numbers, and of course we're going to be focusing on sets of numbers. An element is any item that's in a set. So if I have a set of numbers, each individual number then becomes an element. So if we have our set written as this, A equals the set 1, 2, 3, 4, then we call that roster form because all of the elements in the set are listed. So if you list all the elements out, then you're in roster form. Now, to show that an element is part of a set, we use this symbol that's read is an element of. So if I write 2 is an element of A, that's the way that's written, and of course this is the way we would read it. 2 is an element of A. In addition, we would say, if we have this set A, that 5 is not an element of A because it is not in our set. Our set is said to be a finite set because the number of elements in the set can be represented by a whole number. So if you notice here in set A, we would say that's finite because there are 4 numbers in our set. If you can't represent that by a whole number, then we call it an infinite set. We also talk about a set that has no elements, and that's called the empty set, which you can write two different ways. The brackets with nothing in it, or a 0 with a slash through it. Another way that we can describe sets is called set builder notation. Now when you first see this, it looks a little strange, but it's actually really easy to understand. An example of a set builder notation would be this. Say that S is equal to, and then there's the way we write it. Now, here's the way this is read. The first part of the set notation is the variable that we're going to be talking about. So this would be about variable x. Then you have the rules or rule that would describe it. So we actually have two rules here. Our rules are that x has to be less than 5 and that x has to be an integer. And then this symbol that's just like a straight bar, maybe half of an absolute value symbol, is read such that. So if we look back, this is the way we would read this. We would say that set S is x such that x is less than 5 and x is an integer. Now, one of the things that you can do once you start learning about sets is to start looking at combinations of sets, and that's where we're going to talk about unions and intersections. A union symbolized by what appears to be a U and can be written as A union B, is where you're taking 2 or more sets, you're combining them in such a way that any element that's in A union B is either in A, B, or both of them. So as long as it appears in any one of those two groups, then it can appear in the union of the two groups. A different type of combination is called an intersection. So we symbolize the intersection with an upside down U. We would read this as A intersect B. It's 2 or more sets where the elements have to belong to all of the sets. So in this case, if we have 2 sets, to be in the intersection of A intersect B, we would have to be in both A and B. Let's look at an example. Say that A is the set 1, 2, 3, and B is the set 2, 3, 4. Then the numbers that would belong to A or B is any number that's in either of those two sets. So notice that in the first set we have 1, 2, 3, so that's the first 2 sets of our union. And then any element that's in B that was not in A, which would be 4, would also be in the union. So you're just taking the two groups, making them into one big giant group. Now, if we're doing an and problem, A and B, then it has to be numbers that are in both of those groups. So if I look at my two sets, the numbers that appear in both of those groups are 2 and 3. So the intersection of A and B would be the set 2 and 3. You can also look at this in terms of a Venn diagram. If you look at the part where the two sets overlap, that part is your intersection. And if you look at all the numbers, then that is your union. Now we're going to look at some intervals and how to write things in what we call interval notation. And one thing that's really important that you remember is that infinity and negative infinity are not numbers. It just means that we are looking at a way to write all the real numbers so that they don't end, either in a positive direction or a negative direction. So that if we're looking at the positive direction, we would say that that would go towards positive infinity. And if we're looking in the negative direction, we would say it would go towards negative infinity. We need to take a moment and just talk about what we call open and closed intervals. Here's different types of notation. When we have the notation A comma B with parentheses on both ends, what that means is that the first number is the starting point of your interval. The second number is the ending point of your interval. And if you have parentheses, it means that it is not including those points. So parentheses are non-inclusive. And if you have a bracket, those are inclusive. It means that you can contain or can use those points as points in your interval. So what we have here is we have 3 different ways to represent the same sets of numbers. Now what I'm going to do is I'm going to go through, you should take some time to look over the video, but I'm going to go through just the terminology of whether this is closed, open, half open. So if we look at our first interval, we're talking about numbers from A to B, and we're not allowed to use A and B. Now, one way you can draw that on a number line is that you would have an open circle at A because it's not including A, an open circle at B because it's not including B, and then we want everything between those two to be included, so we would shade that. Now, I will point out that this is one way to do this. Our textbook does not use that notation. Rather than using the open circles, they use parentheses and brackets. So you would see this in our book as a parenthesis there and a parenthesis there. This is called an open interval. In the next one, notice that we have a closed dot at B and an open dot at A, but we're still including the points between them. So again, in our book, we would have a parenthesis here and a bracket here. Because one of those ends is closed, the other is not, we call this a half open interval. In the second one, we've just reversed it. It's a closed on one end at A, open at B, so this is another half open interval. For the next one, notice that both points A and B are included, so those would have brackets for us, and that's a closed interval. In the next example, you have infinity, so we've got an open interval at A, and then we're going on to infinity, so this again would be a half open interval. In the next example, B is open, and you're going towards negative infinity, so that one is also half open. In the next example, we have a closed interval at A, but it's open towards infinity. It just keeps going, so that's half open. We have a closed dot at B, but we go towards negative infinity, so that's half open. And then the last one, you have going from negative infinity to positive infinity, and that one is open. Now let's look at how we would graph this open interval from 3 to infinity. Since 3 has a parenthesis, it means it's not included. So we're going to go to 3 and we're going to put a parenthesis. But we're going to go out towards infinity, so we just come out here and shade this. And then we'd want to shade the end to show that we want that to go on towards infinity. Now let's look at the half open interval from 0 to 4. Well, we don't include 0, so we're going to put a parenthesis there. But we do include 4, so we'll put a bracket there. And we want all the points between those two. Now we want to write this notation, or this line graph, using algebraic notation, and then state what kind of interval it is. Well, without even writing it, we can tell that it's going to be half open because we are going towards infinity on this end. And even though this is closed at 1, it's still going towards infinity. So how would I write that in algebraic notation? Well, I would say we'll use the variable x is greater than or equal to, and we know that because of the bracket that it's an equal to problem. If it was a parenthesis, it would just be a greater than, and it's greater than or equal to 1. We could also write that in interval notation, and let's do that even though they don't ask. In interval notation, we would write that as 1 with a bracket, comma, and then our graph goes to infinity, parentheses. Let's represent the following using interval notation. So we're going to go from -3 to +1, and both of those ends are open, so we'll put parentheses there. We could also write that, again, even though it doesn't ask us to, in algebraic notation by writing it this way. X is all the numbers between -3 and 1, but we're not including them, so we just make them less than symbols and not less than or equal to. Now let's look at combinations of sets. What if I wanted to graph x is greater than 5 or x is less than or equal to 4? So I'm going to do this in different colors. Let's do our first one, x is greater than 5. Well, that would look like this. We come out here at the end where 5's at. We put a parenthesis because we want to not include 5, and we want to go towards infinity. And that would be what x is greater than 5 looks like. X is less than or equal to 4 would have a bracket there. And then we want to go towards negative infinity. Now remember, when it's an or, what we do is we just combine those two graphs together and make one big graph or one big interval. So we're just going to put our first part of our graph is up here. Our second part of our graph is here. And there would be our final graph of x is greater than 5 or x is less than or equal to 4. Let's look at an intersection problem. So again, we'll do this in different colors. X is less than or equal to 2. So if I do x is less than or equal to 2, I'm going to put a bracket at 2. And we want everything less than that, so we're going to shade down this direction towards negative infinity. X is greater than or equal to 0. So we'll go to 0, we'll put a bracket, and we want everything above it. Now, because this is an AND problem, we want the part that is in both of those groups. So imagine that what we're looking for is the part that falls between both of those. So our final solution for the AND graph would be that we would use 0 because 0 is included in both of the two separate graphs, up to 2, and 2 is included in both of those, and we would shade the part that was between those.